So welcome to CECS 228. We're going to be starting a new module, which is proofs, starting with part 1. So part 1 deals with the rules of inference. At this point, we've seen several examples of mathematical discussions and subproofs. We're now going to focus on developing the skills necessary to construct valid arguments and eventually also proofs. So first, we're going to take a look at how the rules of inference help us distinguish between a valid and invalid conclusion. Then we're going to take a look at some common types of proofs that use these rules of inference. And then finally, we're going to take a look at the mathematical induction and strong mathematical induction type of proof. This one is useful when we're trying to prove the correctness of an algorithm, in particular those algorithms that have recursive definitions in them. So let's get started, and we'll do so by taking a look at these next definitions. So starting with argument. An argument in propositional logic is a sequence of propositions, and these could be compound propositions. All but the final proposition in the argument are called premises or hypotheses, and then the final proposition is called the conclusion. An argument is considered to be valid if the truth of all of its premises implies that the conclusion is true. So written with logical connectives and variables, this means that if you have an argument composed of n propositions, we'll call them P1, P2 through Pn, and some conclusion C, then the argument is going to be valid when the conjunction of the premises implies that the conclusion is true. Or in other words, if this implication is a tautology. Now, an argument form in propositional logic is a sequence of compound propositions that involve propositional variables. So basically, an argument form is just taking the English argument and translating it into variables and connectives. Right, so let's apply that with example number 1. We're going to consider 3 statements, and we're going to identify the premises, the conclusion, and whether or not they form a valid argument. Okay, so if you have access to the network, then you can change your grade. You have access to the network, you can change your grade. So these first 2 would be considered premises. Oops, I should say premises. And this last one would be considered the conclusion. Now, whether or not they form a valid argument, well, we said if the argument will be valid if, assuming that the premises are all true, imply that the conclusion is also true. So in order to check that, I'm going to be translating it into an argument form. The first statement, if you have access to the network, then you can change your grade, will have 2 independent proposition, or not independent, but not completely independent, because we do have if then. But what I mean is we'll have 2 variables. First one, you have access to the network. Second one, you can change your grade. And so the first premise number 1, would be if you have access to the network, if P, then you can change your grade, then Q. Second premise, you have access to the network. That's just P. And then the conclusion, or what we want to check, is also true, is you can change your grade. Okay, so conclusion Now I'll actually use different color for it since I started using red for the conclusion. The conclusion is Q. And actually, when we are writing it in argument form, we like to use these three dots that form kind of like a triangle. That actually means therefore. And so that symbol means therefore. So we're saying therefore Q. So we want to see if this is a valid argument. And the way we said we check that is by assuming that the premises are true. So if P implies Q is true and P is true, does that mean that Q is true? Okay, so that's the question mark at the moment. Well, let's see. If premise 2 is true, meaning if P is true, then the implication in premise number 1 becomes true implies Q. Okay, so from premise 1 and 2, I'll just call them 1 and 2. So from 1 and 2, we have that true implies Q is true. Now, in order for true implies Q to be true, that forces Q to be true as well, because if you remember from the truth tables, true implies false was a false statement. It was that example, that example of a promise, right? If my condition is true, but the expectation is false, then I made a false promise. Okay, so in order for the promise to be true, when the condition is true, the delivery of my promise also has to be true. So this forces, so from 1 and 2, true implies Q is true, forces Q to be true. So i.e., the conclusion Q is true. Okay, so it does follow from premise 1 and 2. So i.e., the conclusion is true. That means that this is a valid argument. This is one of several examples of valid arguments that you can go ahead and check form a tautology. So this first one that we just saw, P implies Q and P implies, so therefore Q, that type of argument is called modus ponens, and it's a rule of inference. Other rules of inference are, for example, if you assume negation Q and P implies Q, then you're allowed to conclude negation P, and that's called modus tollens. And well, these other ones I'll let you go over on your own, kind of read to yourself and digest, but we will be seeing them in the following examples. So starting with example number 2, which is asking us to use the rules of inference and propositional variables to express the following in argument form. Then we have to determine whether the argument is valid and if the conclusion is true. So if it snows today, then we will go skiing. It is snowing today, we will go skiing. So remember, these first two have to be the premises. In an argument, everything but the last statement is a premise. So these are premises. And then this last one is the conclusion. So we'll start by defining P as it is snowing today, or it snows today. And Q will be, we will go skiing today. I'll leave out the today, but we'll write the dot, dot, dot. Okay, so for premises, the first premise, if it snows, then we'll go skiing. That's P implies Q. Second premise, it is snowing today. That's P. And finally, the conclusion, we will go skiing. So therefore, Q. Well, this is definitely a valid argument. This is an example of modus ponens, which we just discussed. So because this whole argument form follows modus ponens, this is a valid argument. And we've answered one of the two questions. Is the argument valid? Second question, is the conclusion true? Well, the conclusion will be true if the premises are true, meaning if it is snowing today, and if the implication is also true. So that's what we're going to write here. The conclusion will be true if the premises are true. Okay, but at the moment, since, well, this is a hypothetical, we don't really know if it is snowing today, or if you want to apply it for today actually. Well, if it's not snowing today, then we can't really say that the conclusion is going to be true. But since it's a valid argument, the truth of the premises implies the truth of the conclusion. Let's take a look at another example. Use the rules of inference and propositional variables to express the following in argument form. And is the argument valid? Is the conclusion true? So again, we'll start by defining some variables for our propositions. So if the square root of 2 is greater than 3 over 2, then the square root of 2 squared will be greater than 3 over 2 squared. So I see two propositions here. The first one being the statement that the square root of 2 is greater than 3 over 2. And the second statement being that the square root of 2 squared will be greater than 3 over 2 squared. And then we know that the square root of 2 is greater than 3 over 2. That's P. Consequently, the square root of 2 squared is greater than 3 over 2. That's Q. So again, these first two are going to be the premises. This last one is going to be the conclusion. So I'll just draw some curly braces here to separate premises from the conclusion. Premise number one is if square root of 2 is greater than 3 over 2, so if P, then Q. The second premise is it's P. And then the conclusion square root of 2 squared is greater than 3 over 2 squared. That would be Q. Okay, so one more time we see that modus ponens argument form. So this one is valid. But here's what's different in this example. Is the conclusion true? The conclusion is that the square root of 2 squared is greater than 3 over 2 squared. Okay, so let's check that out. The square root of 2 squared, that's just 2. And 3 over 2 squared, that's a 9 over 4, which is going to give you a 2.25. So 2 being greater than 2.25, because that's what this is claiming, right? Square root of 2 is greater than 3 over 2 squared. That is false. So the conclusion here is false. So we might say, well, wait a minute, but we just said that the argument was valid. How is it that we built a valid argument but came up with a false conclusion? Well, again, let's think about what does it mean for the argument to be valid? The argument is valid when, if you assume that the premises are true, then the conclusion is true. So if the conclusion turned out to be false in a valid argument, that means that one of the premises must have failed in being true. Okay, so let's check. The easiest one to check is this single premise, the single proposition, the square root of 2 is greater than 3 over 2. So here, let me just write a question for ourselves. Why is the conclusion false if the argument is valid? Well, let's see. The square root of 2, if you punch it into your calculator, so square root of 2, again, square root of 2, that's going to give us approximately a 1.4. Whereas 3 over 2, that's exactly a 1.5. So 1.4 being greater than 1.5, which is the claim or the premise P, is a false statement. So since premise number 1, actually it's premise number 2 fails, the conclusion also fails to be true. So that's something to keep in mind, that you can have a valid argument, but if one of your premises is not true, then your conclusion is not going to be true either. Okay, let's take a look at example number 4. State which rules of inference are being used in the argument. And for part A, we have, if it rains today, then we will not have a barbecue today. If we don't have a barbecue today, then we'll have a barbecue tomorrow. Therefore, if it rains today, we'll have a barbecue tomorrow. So just, we're going to be writing it in argument form. That way we can compare against the rules of inference. In order to do so, we need to define variables. And since there's quite a few statements here, I'm simply going to be highlighting and then labeling the variable right above it. So if it rains today, I'm going to use P for that. We will not have a barbecue today. I'll use negation Q for it, since we do have not. If we do not have a barbecue today, so that's still negation Q. Then we will have a barbecue tomorrow. That's going to have to be a different variable. Let's call it R. Therefore, if it rains today, that's P. Then we'll have a barbecue tomorrow, that's R. So let's identify our premises. The first one is if P, then negation Q. Second premise, if negation Q, then R. Therefore, that's signaling a conclusion already. Okay, so therefore, if it rains today, if P, then we will have a barbecue tomorrow, then R. Okay, so let's take a look at the rules of inference, and I've actually printed those a little bit larger, because I know the one in the lecture notes is a bit small. But we're looking for something that involves a rule of inference that involves two implications. And if you take a look at the table, there's really only one that has two implications. That's hypothetical syllogism. So under hypothetical syllogism, if you have P implies Q, and this conclusion Q is the premise of the second implication, Q implies R, then you can make the connection between P and R. P will be the premise of the final implication, and R will be the conclusion of the final implication. Okay, so it's almost like this connection kind of looking like a Z. So what we have is very similar. The only difference is that instead of having a Q, we have negation Q. But still, it's the same idea, right? With when we were talking about the equivalence laws, it's not that an argument or a statement has to fit exactly the way the rule has to look exactly the same way that the rule looks. We can replace these variables, okay, P and Q, by compound propositions, which is happening here. We have negation Q, that's allowing us to conclude P implies R. So this is an example of hypothetical syllogism. Right, next example. It is below freezing now, therefore it is below freezing or raining now. Let's define some variables. It is below freezing now will be P. Therefore, it is either below freezing or raining, so this is still P. And then it is raining now. We'll define a different variable for it. We'll have Q. So we really only have one premise, and that is the premise P. It is below freezing now. Because right after that, we come across the keyword therefore, which signifies conclusion. Therefore, P or Q. Okay, so let's take a look. We're looking for a rule of inference that begins with a single premise and concludes the disjunction of that premise with a different premise. So if you take a look at addition, that is the one that fits exactly the form we have, right? If you have premise P, then you can conclude P or Q. This is an example of addition. Okay, one more part to this example. It is below freezing and raining now, therefore it is below freezing now. We'll use the same P and Q that we did in part B, since they have the same propositions, but now the premise is different. The premise would be P and Q, therefore P. Right, so if you go again, look at the rules of inference, which starts with a conjunction and ends with a single proposition, that would be simplification. If you have P and Q, you're allowed to conclude P. So this would be simplification. Okay, so example number 5, they're actually telling us which rule of inference they want us to use. They're asking us to use resolution to show that the hypotheses Jasmine is skiing or it is not snowing and it is snowing or Bart is playing hockey imply that Jasmine is skiing or Bart is playing hockey. So again, let's define some variables here. We'll take Jasmine is skiing as P. It is not snowing since we have that negation. I'll write this as negation, oops, actually wrong pen, negation Q. It is snowing or Bart is playing hockey, so it is snowing would be simply Q. Bart is playing hockey, we're going to need a different variable for, so we'll define that to be R. And the goal is to show that Jasmine is skiing or Bart is playing hockey, so that would be P or R. Okay, so let's start with the premises. Premise number 1, Jasmine is skiing, P or, it's not snowing, not Q. Second premise, it is snowing, so Q or Bart is playing hockey, or R. And now let's take a look at the rules of inference. Actually, before we do, let me do one one manipulation here with the first premise. Since we have disjunction and disjunction is commutative, I'm going to rewrite this into the negation Q or P. Right? The order doesn't matter when we're talking about or. And this bottom one, I'm not making any modification. I'm just simply bringing over so that they align and that we can compare it a little bit better with our rules of inference. Now they did say use resolution, so let's look down at resolution. Resolution says when you have P or Q and negation P or R, it's almost as if these two cancel out and you're just left with Q or R. Okay, so you're allowed to disregard the P and negation P and conclude simply Q or R. So if we take a look at what we have here, we have negation Q or P, Q or R, so that's going to allow us to conclude P or R. And this is by resolution. Now, what does P or R claim? P would be Jasmine is skiing. R would be Bart is playing hockey. So that is this statement. Jasmine is skiing or Bart is playing hockey. Let's take a look at example number 6. Example number 6 is asking us to show that the premises P and Q or R and R implies S imply the conclusion P or S. Okay, so again, these here would be the premises, or what we're allowed to assume. And then we're going to try to make it to P or S. Okay, so our goal is to show this conclusion. So what I'm going to do here is I'm actually going to create a table with two columns. The first column is just going to have some statements. The second column is going to have justification for those statements. So let's start with, maybe let's go ahead and start with just writing down the two premises. So first premise is P and Q or R, and that's premise 1. Second premise is R implies S, that's premise 2. And since we are trying to get to P or S, that means that the R's have to go away somehow. And if you recall, there was one rule of inference that allowed us to do that whenever we had disjunction, and that was resolution. But for resolution, we need to have two disjunctions, and the same variable show up in both, but one of them has to be negated. So what I'll do here is I'll change this implication into the disjunction of negation R or S by applying table number 7. Okay, so table number 7 of the logical equivalences, this first one reads, if P implies Q, then negation P or Q. So let's give that a try. We'll have negation R or S, and this is by table 7.1. And then just so that the negation R and R align, which they don't have to, you can skip this step, but I'll write it just to be complete. Okay, I'll just flip the order. This is a commutative law. Apply it on 3. And statement number 3. Okay, and now what we'll do is we'll forget about these two here. Actually, that's a little too thick, but we'll just forget about 2 and 3. Focus on statement number 1 and statement number 2. We have these two disjunctions. One of them involves R, the other one involves negation R. So by resolution, what we're allowed to conclude is that P and Q or S. Okay, this is by resolution on 1 and 4. These two. Okay, that brings us a little bit closer, but we're not quite at the goal yet. So in order to have P or S, what I'll do here is I'll use my distributive law. Now, if you have your table of logical equivalences, distributive law would be the 4th one from the bottom. And it says that if you have disjunction in conjunction, it's like taking this disjunction P and distributing to each of the variables inside, or each compound proposition inside if you have something a little more complicated than Q and R. But basically the result would be P or Q and P or R, which is this portion here. Okay, so let's take a look here. We distribute the or S, we'll have P or S, and distribute the or S to the Q, so we'll have the Q or S. This would be by distribution. We're actually very close to the conclusion now. This last one is actually going to be just a statement. P or S. Let's say why am I allowed to conclude P or S? Go to the rules of inference. Rules of inference. If you take a look at the simplification rule, it says if you have the conjunction of two propositions or two compound propositions, then you're allowed to conclude P or either one of these. So for instance, if this means I'm wearing purple and I'm wearing black, then we can conclude that I'm wearing purple is true, right? So same thing here. If we have some compound proposition and a second compound proposition, we're allowed to conclude the first compound proposition. So this is by simplification. Okay, for this next example, example number 7, I've gone ahead and defined some variables that are going to help us with the directions. So the directions read, use resolution to show that the premise is, it is not sunny this afternoon and it is colder than yesterday. We will go swimming only if it is sunny, and if we do not go swimming, then we will take a canoe trip. And if we take a canoe trip, then we will be home by sunset, lead to the conclusion, we will be home by sunset. So I'm using P, Q, R, T, and S in the following way. P is, it is sunny this afternoon. I've just didn't complete it, just dot, dot, dot. It is colder than yesterday, would be Q. We will go swimming is R, and T is we will take a canoe trip, and then the last one, we will be home by sunset, is S. So with these definitions, let's go ahead and write out what the premises are. Okay, so the first premise, it is not sunny this afternoon, and it is colder than yesterday. So it is not sunny would be negation P, and we have and it is colder than yesterday, that would be Q. Next premise, we will go swimming only if it is sunny. So remember, the only if is premise, only if conclusion. So we will go swimming would be the premise, and that is given by R, implies it is sunny, so that would be P. Next premise, if we do not go swimming, so not go swimming would be negation R. If we do not go swimming, then we will take a canoe trip. So then T. If we take the canoe trip, so T implies, then we will be home by sunset. So that implies S. So it's in 4 different premises. Now we have to use those premises to lead to the conclusion, we will be home by sunset, which is simply S. Okay, so the goal is to show that these lead to therefore S. Okay, so what I'll do here is similar to what we have in example number 7, a table with 2 columns, and I'll separate these definitions and premises from that table. A table with 2 columns where the first column will be the statements and the second column will be the justifications for those statements. Right, so let's give it a try. I'll start with, they do say use resolution. Okay, so let's take a look at what resolution was again. Resolution referred to when you have 2 disjunctions, one of them, 2 disjunctions using the same variable, but one of them is negated. When that happens, you can cancel these out and end up only with Q or R. So in order to be able to use resolution, I need to have disjunction, which I don't have at the moment. So what I'll do is I'll start by changing all of these to disjunction by using table 7.1. Okay, so my first statement is going to be negation R or P, and that is table 7.1 on premise number 1, actually number 2. And I'll use P2, short for premise 2. I'll do the same thing for number 2. For premise number 3, but statement number 2. So that's going to be R or T, because we would have negation of negation R, that simply becomes R or T. That's table 7.1 on premise number 3. Now if we take these two together and apply resolution, these would cancel out and we would end up with P or T. So we have P or T by resolution on 1 and 2. Okay, then what? Then what I'm going to do is apply table 7.1 to this fourth premise. And a lot of this, this is the approach that I'm taking right now, the steps, the order of the steps. But maybe if you were working out this problem, you might come up with a different order of the steps, or even maybe different applications, and still make it to the goal. And that is okay. There's more than one way to approach these types of problems where you're trying to show that a conclusion results from some premises. Okay, but in this case, I'm going to take premise number 4, change it to negation T or S, and this is by table 7.1 on premise 4. And now if we take 3 and 4 together, 3 has T, 4 has negation T. Both of them are disjunctions, so we're allowed to conclude P or S. This is by resolution on 3 and 4. And again, let's think about what we're trying to get to. We are trying to get to S, simply S. And currently as it is, we are not allowed to conclude just S, because the only way that we'd be able to do that would be if this were a conjunction. But there is one premise that we haven't brought into the picture yet. That is premise number 1. So let's bring it in, and then we'll see if there's any way or anything that we can do here to help us out. So I'll bring in negation P, and Q. Well, that's simply premise number 1. Now what I can do is conclude negation P, right? So it's kind of like I'm not wearing purple, but I am wearing green. Therefore, I'm not wearing purple is a true statement. But that is a rule of inference. The rule of inference that we're taking a look at is simplification. When you have the disjunction of two propositions, you're allowed to conclude one of them, or either one of those. So this would be simplification on 6. Okay, and so now that we have it in this form, we are actually pretty much at the conclusion. How do we know that? Well, I have P or S. I also have negation P. If we take a look at the rules of inference, pay attention to disjunctive syllogism. We have P or Q, negation P, therefore Q. So if you have the disjunction of two propositions, but you also have the negation of one of those two propositions, then we're allowed to conclude the second proposition, the one that's not being negated. So in our case, Since we have P or S, negation P, we're allowed to conclude S. Actually, this is purple, so let me just change the color of my pen. So we can conclude S. And this is by disjunctive syllogism. On 5 and 7. Okay, so we're taking these two statements together to get S. So it does lead to the conclusion we will be home by sunset. Next, we get to consider some invalid arguments. By the way, if an argument is invalid, then it is called a fallacy. And in this case, they want us to show that the argument P implies Q and Q, therefore P, is a fallacy. This is actually a common type of incorrect reasoning that is called the fallacy of affirming the conclusion. An example would be something like, I don't know, if I oversleep today, then I'll miss class. I missed class, therefore I overslept. That would be a fallacy. And here's a reason, well, at least in this example that we're placing, just because you missed class does not mean that you overslept. Maybe you missed class because you didn't catch the bus on time because you decided to have a coffee, for instance. And so it doesn't mean that we overslept. It simply means that there was some other reason for which we missed our class. So we want to show in general that if we form this argument that, that it is going to be invalid. And so let's take it back to the definition of what valid was. Valid argument meant that when you assume the truth of the premises, they imply the truth of the conclusion. So let's assume the truth of the premises and see if that forces the conclusion to be true. If it doesn't force a conclusion to be true, then it is not a valid argument. Okay, so let's see. If we assume, well, first let's write what are the assumptions. We're going to assume P implies Q is true. And Q is true. All right, putting these two together, so by 1 and 2, we have that P implies true is true. So what implies true makes the whole implication true? Well, true implies true is true, but also false implies true is true. If you go back to the truth tables, that's one of the things that we learned. So in this case, which in turn means P can be true or false, and still satisfy the truth of the implication. So because it can either be true or false, then it is not a valid argument. It would need to be only true. So, let me just go ahead and highlight the important part, is that P can be true or false. And therefore, this is an invalid argument. And just to stress this a little bit further, what that means is that there could be a case in which the premises are true, but the conclusion is false. Okay, so I'm just going to write that in. So i.e., there could be a case, or there is a case, in which the premises are true, but the conclusion, which is P, is false. So that's invalid. That's not allowed. Okay, next example. Is the following argument valid? If you do every problem in the book, then you will learn discrete mathematics. You learn discrete mathematics, therefore you did every problem in this book. Okay, well, if we write this in propositional variables and connectives, let's say that you do every problem in this book is P, and you'll learn discrete mathematics, that's our Q. And so the argument form of this would be first premise, if P, then Q. Second premise, you learn discrete mathematics, so that's Q. And then the conclusion is that you did every problem in this book, so therefore P. And well, this is an example of the fallacy of affirming the conclusion. This is an invalid argument. So altogether, this is fallacy of affirming the conclusion. Okay, let's take a look at example number 10. Let P and Q be as an example 9. So P is you do every problem in this book. In fact, let me go ahead and have example number 9 up. I didn't clearly label it, so let me just do that now. This will be P, this is Q. So if the conditional statement P implies Q is true, and negation P is true, is it correct to conclude that negation Q is true? So in other words, is it correct to assume that you did not learn discrete mathematics if you did not do every problem in the book, assuming that if you do every problem in this book, that you will learn discrete mathematics? Okay, so that's quite a mouthful. Let's first try to write it down into premises and conclusion. So if the conditional statement P implies Q is true, so that's our first premise. And negation P is true, so that's our second premise. Are we allowed to conclude that negation Q is true? So conclusion. Negation Q. The question is this a valid argument? And well, let's see. Remember, for valid, we're going to check if the truth of the premises implies the truth of the conclusion. So we're going to start by assuming that this is true. and that negation P is true. And so from premise number 2, we can say that P is false because negation P is true. So P has to be false. And then if we now join that conclusion to premise number 1, so from premise number 1, that means that false implies Q is true. Now, when is false implies Q true? False implies something is true, holds when we have false implies false, but it also holds when false implies true. But the more, well, okay, let me just state those down. This means Q can be true or false. Okay, but here's a problem with Q being true. So, i.e., there is a case in which the premises can be true. Premises but negation Q, so if Q is true, then negation Q will be false, which is the conclusion. And that is invalid. This is an invalid argument. Okay, in fact, this is a common fallacy, and it's the fallacy of denying the hypothesis. It has a special name. So if you ever see this argument, P implies Q, negation P, therefore negation Q, that is a fallacy. It's an invalid argument. It is a fallacy of denying the hypothesis. Okay, now to extend the rules of inference to quantified statements, these are the rules which we've had a little taste of when we saw the proofs for De Morgan's laws for quantified statements. But more specifically, if you have as a premise for all x p of x, then you're allowed to conclude p of c. So basically, if for every element in the domain p of x is true, then it's in particular true for c, who is part of the domain, or which is part of the domain. And that's called universal instantiation. If you have that P of C is true for an arbitrary element C, though since C doesn't have anything special about it or any special conditions that it meets, then we're allowed to conclude the same thing about every element that is part of the domain because C is an arbitrary element. So we're allowed to conclude for all x P of x, and that would be universal generalization. Next one, if there exists an x such that P of x is true, then it's true that P of C is true for some element C, and that's existential instantiation. And finally, if P of C is true for some element, then there exists an x such that P of x is true, is also a true statement, and that's called existential generalization. So for example 11, they want us to show that the premise is everyone in this discrete mathematics class has taken a computer science course, and Marla is a student in this class. Imply the conclusion that Marla has taken a course in computer science. So in order to build this argument, I'm first going to translate it into propositional functions and quantifiers. So here we have everyone in this discrete mathematics class has taken a computer science course, everyone meaning for all, and then in this discrete mathematics class, that's going to require a propositional function. So I'm going to define d of x as x is in this discrete math class. And we'll need another propositional function to define has taken a computer science course. So let's see if x express that. The domain for both of these functions, I'll go ahead and write it as students in the school. Yeah, so that now if we want to write the premises, we would have premise number 1. Everyone in this discrete math class has taken a computer science course. So for every student in the school, if the student is in this discrete math class, then the student has taken a CS course. And then the second premise is that Marla is a student in this class. So D of Marla is a true statement. And finally, we want to reach the conclusion Marla has taken a course in computer science. So the goal, because it's not our conclusion yet, but it will be, is that Marla has taken a computer science course. C of Marla. Alright, so we're going to build the argument, and unfortunately I've run out of space, so I'm going to include the rest on a sticky note. Again, I'll have 2 columns, one for the statements, the other one is for the justifications. Okay, so for our first statement, I'll simply write what the premise is. For all x, d of x implies c of x. So if they're in the discrete math course, then they've taken a computer science course. And this is premise 1, which I'll write as P1. Now, if it's true about every student in the domain, so if it's true about every student in the school, then Marla is a student, right? So I can say it's true about Marla. So D of Marla implies C of Marla. If Marla has taken, if Marla is in this discrete math class, then she's taken a computer science course. So this would be an example of universal instantiation. We went from something that was general to something that was particular, about a particular element in the domain. Okay, so this is universal instantiation. Next thing that I'll write as a statement is that Marla is in this discrete math course. That's a given. That's premise number 2. And now, if you take a look at this, we have implication, Okay, so premise implies conclusion. We are given the premise, so therefore together they imply the conclusion. And this was an example of modus ponens. Okay, so let me just bring back rules of inference. Take a look at modus ponens. If you have P implies Q and P, then you can conclude Q. And to think of this as P and Q, so I have P implies Q, I have P, therefore Q. So therefore C of Marla. And this is by modus ponens. That's how you apply the rules of inference for quantified statements. We'll take a look at some more examples. Show that the premise is a student in this class has not read the book, and everyone in this class passed the first exam. Imply the conclusion, someone who passed the first exam has not read the book. So let's give it a try. I'll define a function for expressing the student is in this class. So C of X will be X is in this class. And something that can express they have read the book so that we can also negate it. So I'll write B of X is X has read the book. And also we need something that can express X has passed the first exam. So I'll have P of X be the statement X has passed the first exam. Now for all three of these, I'll define a domain of students in the school. So now we can write down what the premises are. First one, a student in this class has not read the book. So there exists would be some student or a student. There exists some student in the school, so who is in the class and has not read the book. So and negation B of X. This would be premise one. In fact, I'll go ahead and just write directly onto my table of statements and then justifications. What's the next premise? Everyone in this class passed the first exam. So everyone would be for all, for every X. So for every student in this school, if the student is in this class, then the student has passed the first exam. That's premise number two. What is it that we're trying to reach? We're trying to reach someone who passed the first exam has not read the book. So that would be there exists someone, some student, who passed the first exam and but has not read the book. Okay, so there exists some student X such that they pass the first exam and they have not read the book. This is the goal. So let's see how, what would be maybe the best way to reach that. We first want to make sure that we instantiate these however possible, because we can't apply the rest of the equivalence laws or the rules of inference for propositions unless these have been instantiated. So from these these two premises, I'm actually going to focus on this first premise. It reads, there's someone who is in this class and has not read the book. I'm going to call that someone, let's call them just person A, or student A. So C of A implies, and negation B of A. Okay. So A is a student who is in this class and has not read the book. What we're doing here is existential instantiation. Right, now what else can we do? Well, if we take a look at premise 2, this is something that is true for everyone in the domain, right? For all students in the school, if the student is in the class, then the student passed the first exam. So if it's true about everyone in the class, it's in particular true about the student A, right? So if student A is in the class, then student A passed the first exam. And so what we're doing here is universal instantiation. Okay, what can we do from there? Well, from there, I can change this implication into a disjunction and see if it leads us anywhere. And that would become negation C of A or P of A and so that would be by table 7.1 on my fourth statement. Okay, and then from number 3, I have C of A and negation B of A. So I can simplify. So if it's true that the student is in this class and the student has not read the book, it's true that the student is in this class. This is simplification on 3. Now, why am I saying that? I'm saying that because if the person is in this class, then the statement that the person is not in this class or the person has passed the first exam would mean that the person has passed the first exam by our rule of inference disjunctive syllogism, right? We have P or Q and negation P. It's almost like these two cancel out and we're left with just the Q. So in this case, it's like the negation C of A and C of A cancel out and we're just left with the P of A. So this is disjunctive syllogism. On 5 and 6. What else can we conclude? Well, I'm actually going to continue on a separate sheet. Well, remember the goal. We're trying to get to there is some students such that P of X is true and negation B of X is true. We already have there is some students such that P of A is true. To make it to that same student also fulfills that negation B of X, we can take a look at 3 again. And since this is saying the student is in this class and the student has not read the book, then the student has not read the book by itself is true. So that is also by simplification on 3. Now if we put these two together, because this one's saying the person passed the first exam, this one is saying the person did not read the book, So together, the person passed the first exam and has not read the book. The justification for it is addition, if you look at the rules of inference. Excuse me, not addition, but let's see, conjunction, that's what it is. So we have P and Q. We can conclude P and Q. So this is by conjunction. On 7 and 8. Okay, and so finally, for person A, these two are true. So there exists some student in the school for which they have passed the first exam, and they have not read the book. And this would be existential generalization. Okay, so that was our goal, and we've made it. Now what I encourage you to do here is to go back and give it the English meaning to each of these statements. So this is saying a student there is some student that is in this class and has not read the book. And for every student, if they're in the class, then they have passed the first exam. Now, student A is a student for which they're in this class and they have not read the book, right, from this first statement. And because this is true for everyone in the class, then if student A is in the class, then they have passed the first exam. So what we're saying then is from table 7.1, these two are equivalent. So the student is either not in this class or has passed the first exam, but we know that the student is in this class because of this third statement. So that means that the person must have passed the first exam, and that's this conclusion here. And then because they also have not read the book, we can conclude that independently. And then putting these two together, it means that they have passed the class and not read the book. So therefore, there exists someone who has passed the class, passed the first exam and not read the book. Okay, last example. Assume that for all positive integers n, if n is greater than 4, then n squared is less than 2 to the n is true. Use universal modus ponens to show that 100 squared is less than 2 to the 100. Okay, so let's first write this in variables and quantifiers. So for all positive integers n, I'm going to say for all n, and my domain here is going to be positive integers. The way that is sometimes expressed in math textbooks is the bold Z and then the positive to signify positive integers. Okay, so for every positive integer n, if n is greater than 4, then n squared is less than 2 to the n. Okay, and this is our first premise. And actually, it's our only premise. So again, I'll use statements and then justifications here. So what next? They want us to use that in order to show that 100 squared is less than 2 to the 100. So what I would need to do is first instantiate it for these numbers, right? For n being 100. So 100, if 100 is greater than 4, then 100 squared is going to be less than 2 to the 100. This is by universal instantiation. Since it's true for all positive integers, and 100 is a positive integer, so it's part of the domain. Now, we know that 100 is definitely greater than 4. And that's, for lack of a better justification, that is a math fact. And on the number line, 100 is greater than 4. Now, placing these two together, premise implies conclusion, and premise by modus ponens leads to the conclusion. 100 squared is less than 2 to the 100. Because modus ponens on 2 and 3. Okay, and so that is the end of this lecture. I encourage you to complete the corresponding lab assignment and the relevant exercises to get some more practice with this, and of course ask questions during the lab time and during office hours.